Okay, moving on to problem number 5. So this is looking at a digital communication, digital modulation, and understanding a constellation diagram. So the first question is, how many symbols are possible with this system? So every dot in a constellation diagram is a symbol. So we can just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 symbols. So not too hard. If the baud rate for the system, part B, is 1 kilohertz, what is the bit rate? So baud rate is another term for RSIM, and we'll remember that RB, the bit rate, is equal to RSIM, so how fast are we sending symbols, times how many bits are there represented by each symbol. And our N is going to be log 2 of M, where M is our number of symbols. So log 2 of 16 is going to give us 4, so we're sending 4 bits per symbol. And that means that if we have 1,000 hertz times 4, that gives us 4 kilobits per second. And so that's all we're doing there is just using that equation. We know 1 kilohertz is our baud rate, and that's our sim. We know that log of 16 is 4, so that's our 4 bits per symbol, and that's it. What is the bandwidth? So here we're going to use bandwidth equals 2 RB over N, which is also going to be 2 R sim, and that is 2 times 1,000 hertz, or 2 times 1 kilohertz, which is going to be 2 kilohertz. So we take up 2 kilohertz. And one important thing to remember here in terms of just the concept is that as we increase the symbol rate, we send symbols faster and faster. That increases the bandwidth required for that system. So often things like Wi-Fi will look to increase the number of bits that we're sending instead of increasing the rate that we're sending those bits at, or the rate that we're sending those symbols at. And that's what, going from 256 to 1024 QAM is an improvement from Wi-Fi 5 to Wi-Fi 6. What kind of modulation does this represent? Circle 1. So we can look at the chart here and see that this is all on the same circle, right? We can draw a single circle here, which means a single amplitude. If we have, multiple circles, that represents multiple amplitudes in this constellation diagram, and points around the circle at different angles represent phases. So because we're all on the same circle and we're sort of around the circle at different points, that means we're doing phase shift keying. On-off keying would just be, on the diagram, we would have, 1 amplitude and then or at 0 amplitude and then at some amplitude. Amplitude shift keying would probably be something similar, but we might have 2 things at the same phase. And then, of course, QAM, for quadrature amplitude modulation, we would have different phases and different amplitudes in the same thing. Frequency shift keying we can't really represent with a constellation, so that should never be the answer unless it's just, everything is at 0 on this because it's the same phase and the same amplitude. True or false, a QAM system with the same number of symbols would have the same bandwidth as this, but would be more susceptible to noise. So this is wrong because it should be less susceptible. So the idea being that with a QAM system, we could have this same chart, but we could, split up the in-between phases and put them at a different amplitude. So we could sort of do like this, where, we move around the chart, and we have, one outer amplitude and then one inner amplitude, and that way angles that are very close together can be separated by a different amplitude instead. And so it's easier to tell, whether it's a point on the, at a specific angle, because it also changes amplitude if we're in between 2 points. So that's the idea. It's easier to recognize. So on to problem 6. You are attempting to use jamming to block the enemy from detonating an IED along your path. You believe that the enemy has jury-rigged a garage door remote to transmit the detonation signal. The most common garage door openers operate at 315 megahertz and transmit a maximum of 0.1 milliwatts. The closest the enemy can get to the road without being seen is 100 meters. You would like your jammer to be effective over a 25-meter radius. And sorry about the shifting focus at the moment here. I'm not sure why my camera's doing that. So here we're going to use the jamming equations, and we're going to just figure out how close do we need to be. So let's go ahead and take our factors from the problem here. then maybe let's write down our equation first. So our jammer to signal ratio, we want successful jamming to require a ratio greater than 1, and that's going to be power of the jammer over power of the signal times the distance of the signal squared over distance of the jammer squared. So the usual thing is we can either be louder, more powerful, or closer to jam a signal. So if we're close enough compared to the signal that we're trying to jam, it's fine. If we're loud enough compared to the signal that we're trying to jam, it's also fine. So these are the things we need to figure out what these values are. And we want J of S. So we want J over S to be greater than 1 is the idea. Our P of S. So let's look and see that we've got a transmit power for the garage door opener. So power of the signal we're trying to jam is 0.01 milliwatts, which is going to be, I guess we'll see what the other thing is in. We're trying to find jammer transmitter in milliwatts, so we can leave this in milliwatts because we're solving for a milliwatt value. Our distance to that signal, we're saying that the enemy can't get any closer than 100 meters. And then distance to the jammer, we are assuming that we want to jam things within a 25-meter radius, so distance to the jammer is going to be 25 meters. So we're assuming that, basically, we're here, and this is the jammer. There might be an IED here at 25 meters away, and there might be an enemy, 100 meters from that IED. Trying to trigger it. So that's the idea, is that they're sending their signal there, our jammer is sending the signal there. We're competing to see who's going to be stronger. So these are the values we need. We're going to have 1 is equal to P of J over 0.01 milliwatts times 100, so ds 100 meters squared over 25 meters squared. And then that gives us 100 over 4, or 100 squared over 25 squared is going to give us 16. So we solve for P of J, and that's going to give us 0.000625 milliwatts is the power that we need to get to 1. So we need to be transmitting stronger than that. So P of J, because we want this to be greater than, we actually want P of J to be greater than 0.000625. Okay, so then on to the last part, which is continuing from the previous questions, which of the following strategies could allow your enemy to defeat your jammer? So first up, the enemy could use an older remote technology that uses 390 megahertz. Yes, that will work. And the reason is that the jamming frequency, jamming frequency must equal the signal frequency. So if we are not jamming on the same frequency as the enemy, then we're not going to block that signal, right? They're just transmitting in a different band. It's effectively, frequency spread spectrum at that point, or frequency division that we're doing. So if we're on different frequencies, it's going to work. We're not going to be able to stop it. The enemy can boost their transmitter power. Yes, also works. So you can either be louder or you can be closer, generally. You could add multiple antennas to the receiver on the IED to increase the effective area. Not so much, just because the IED is receiving from both the jammer and the enemy, so if we increase the receiving power of the IED, well, it just receives the jamming signal and the enemy signal better. So that one is a no. And then the last one, the enemy could use camouflage to get closer to the road. Yeah, that'll work, because again, if they are closer, then this signal, the ds squared, is going to be smaller. That's less that we're multiplying by. That means that this is going to be easier to jam, or it's going to be harder to jam, because that signal is louder as you get closer. So think of, if you're whispering to someone and you're really close, it's fine. If the professor's yelling at you from the front of the room, but if they get closer and continue yelling, it's going to be harder to hear the other person whispering. So that's it for these two problems.